Up until now, we've been working our way through the details of a particular robotics problem called forward kinematics. Forward kinematics is the problem where you know the values of the joint variables, for example, the angles of the servos, and what you're trying to find is the position and the orientation or rotation of the end effector. This is very useful for many reasons. For example, in our build, the z equals 0 position is the board. If we would ever calculate that the location of the end effector was at z less than or equal to 0, we would know to avoid that particular set of joint variables because that would cause our end effector to collide with the board. But most often, we're actually trying to solve this problem in reverse. In other words, we know the position or the orientation that we want the end effector to have, and we need to find the values of the joint variables that will get the end effector to go to that position. This problem is known as inverse kinematics. In this video, we'll be learning how to do inverse kinematics. Inverse kinematics, as it turns out, is a somewhat more difficult problem than forward kinematics. Let me start by giving you a brief example of why inverse kinematics is difficult. Here I'm showing the kinematic diagram for the manipulator we've built. We know that we can find the complete homogeneous transformation matrix from the base frame to the end effector frame by multiplying together the two individual homogeneous transformation matrices. In previous videos, we've already found H01 and H12. Let me remind you what those are. Now, to get H02, I could do that by multiplying these two matrices together. In the past, we've stopped at this point and put these matrices into our code. But for this example where I'm showing you why inverse kinematics is difficult, I'm going to multiply them by hand and show you the result. Here's the result of this multiplication. I drew dashed vertical lines to differentiate one column from the next. Remember that the homogeneous transformation matrix contains two parts. It contains the rotation matrix in the upper left-hand corner, and it contains the displacement vector in the upper right-hand corner. In other words, the displacement vector is right here. This first long crazy element is the x position of the end effector in the base frame. The second is the y position of the end effector in the base frame, and the third is the z position of the end effector in the base frame. So let's suppose that I know the xy position where I would like the end effector to be. I could write out two equations like this. I simply take the first equation and set it equal to the x position where I want my end effector to be, and I take the second expression and set it equal to the y position where I want my end effector to be. Now I could plug in two numbers for x and y and solve this system of equations for θ1 and θ2. Do you see why this is a difficult problem to solve? What we have here is not a linear system of equations, but a nonlinear system of equations because of the presence of all of these sines and cosines in these two equations. The only way we could solve this problem would be to do some kind of numerical solution. We can't solve it analytically. Actually, this is one valid way to do inverse kinematics, to write out these equations and then use a numerical method to solve this nonlinear system of equations. But there's another method we can use to actually get an analytical solution, and that's what we're going to be looking at today. This other method is known as the graphical method. I'm going to give you an easier example for the graphical method before we go back and use the graphical method on the manipulator that we've built. Let's suppose that we want to do inverse kinematics on this 2 degree of freedom manipulator. In other words, we want to be able to specify an x, y, z location for the end effector, and we want to solve for theta 1 and d2. We're going to start the graphical method by drawing this kinematic diagram from 2 different views. Either the top view, that is drawing the kinematic diagram in the xy plane, or the side view. In the side view, we just want to be able to look at the manipulator in a plane that includes the z-axis. So for this example, we're going to start by drawing the manipulator in the top view. That is, looking at the manipulator as if we're looking down from the top and seeing the xy plane. So when we look down from the top, we'll see the top of this first joint looking like a circle, like that. We'll see the x0 axis pointing off to the right, and we'll see the y0 axis going up to the top. Now, it's important when we're doing this graphical method that we draw the joint variables not in their 0 position. And in fact, we also don't want to draw them in a position like 90 degrees or 180 degrees. We'd prefer to draw them in a position like 45 degrees. That will make it much easier for us to solve this problem. So if theta 1 was at 45 degrees, we would see its link A2 pointing like this. Then we would see the second joint from the top looking like a square, and the last link in the end effector right here. Now I'm going to draw in the link lengths and the joint variables into this top-down view. In this top-down view, this angle here is theta 1. And D2 is over here. This distance is the link length A2. And this link here is A3. Now, the graphical approach to inverse kinematics relies upon us finding triangles that we can use to write relationships between the joint variables and the xy position of the end effector. It takes a little bit of trigonometry experience and just some experience solving these problems to help you see which triangles are going to be useful. One of the triangles that is basically always useful is this triangle that I'm drawing in purple right here. This is a triangle that tells us the position of the end effector in the base frame. This distance here is y02, the y position of the end effector in the base frame. And this distance here is x02, the x position of the end effector in the base frame. In inverse kinematics, x02, y02, and z02 are the inputs. Those are the things that we know at the start of the problem. That's why this particular triangle is useful to us. We already know 2 of the sides, x02 and y02. Next, I need to write some triangle relationships to get some equations. There really are 3 kinds of triangle relationships that are going to be most useful to me. Number 1 is the Pythagorean theorem. Remember that the Pythagorean theorem is like this. If you have a right triangle and the 2 legs are called A and B and the hypotenuse is called C, this says that A squared plus B squared is equal to C squared. The Pythagorean theorem only works if you have a right triangle. The second triangle relationship that will be useful is SOHCAHTOA. SOHCAHTOA is the acronym that many of us learned in high school or grade school that helps us remember the sine, cosine, and tangent relationships. For example, if we have a triangle like this, and we call the sides A and B, and this angle is theta, we know that the sine of theta is the opposite over the hypotenuse. We'll call the hypotenuse C. The cosine of theta is the adjacent over the hypotenuse. And the tangent of theta is the opposite over the adjacent. These two things both work only if we have a right triangle. Our third option is the law of cosines. The law of cosines works even if our triangle is not a right triangle. Let's call this angle alpha, and we'll call these three sides A, B, and C. The law of cosines says that A squared is equal to B squared plus C squared minus 2 BC cosine alpha. Now, back at this example we're working through, which triangle relationship among the three that we have available to us should we use? Well, we have a right triangle, so we can use 1 or 2 in addition to 3. Let's start by using the Pythagorean theorem. So x02 squared plus y02 squared is equal to the length of the hypotenuse squared. What is the length of this hypotenuse? The hypotenuse length is A2 plus A3 plus D2 squared. Now, in inverse kinematics, we're trying to have x and y be the input, and we want to solve for the joint variables, which in this equation is D2. So I need to rearrange this equation a little bit to solve this for D2. I'll start by square rooting both sides. Now I'll solve for D2 by subtracting A2 and A3 from both sides. Now I have a joint variable on the left, and on the right I have only things that I know, the values of the link lengths and our input x and y. So I'm done with this equation. Now I'm not done with the problem yet because I still need an equation for theta 1. To get an equation for theta 1, let's use SOHCAHTOA. When we're using SOHCAHTOA, anytime I can use the tangent, my solution will end up being more robust than in other cases. So I'll write this equation. The tangent of theta 1 is equal to opposite over adjacent, y over x. And now I'll solve for theta 1. I have a joint variable on the left, and on the right I have only things that I know. So this equation is finished. Also, I'm finished with the whole problem because now I have one equation for each joint variable. Let's do one more easier example before we go back and do a hard one. Okay, let's do inverse kinematics for this manipulator. This manipulator starts with a prismatic joint and then has a revolute joint attached to it. Let's start by drawing this manipulator from the top-down view. From the top-down view, the first joint will look like a square. Then we'll have a circle for the second joint, and then when I show the last link, I'm going to draw it as though theta 2 was 45 degrees. In this picture, this is the Z0 axis, and this will be the X0 axis. We can't see Y0 in this picture because Y0 is pointing straight up at our eyes. We're looking down at this manipulator. The joint variable D1 is here, and the joint variable theta 2 is right here. This is the length A1, and this is the link length A3. Okay, now the first thing we need to do is identify the end effector position in this picture. The end effector is right here, so now I'm going to make a triangle that shows its position. It's tempting to use the link length A3 as the hypotenuse here, but that isn't true if we're trying to show the position of the end effector. The 0, 0 position is all the way back here, and so the triangle that shows the position of the end effector is this triangle. This distance here is the X position of the end effector in the base frame, and this distance here is the Z position of the end effector in the base frame. Now, using this triangle and any other triangle relationships that we need to draw in, we need to find some relationships that say D1 equals something, where this something only includes things we know on the right-hand side, and we need another equation that says theta 2 equals something. Remember that we have three options at our disposal. We have the Pythagorean theorem, SOHCAHTOA, and the law of cosines. Sometimes the one triangle that shows the position of the end effector isn't enough to get us all the way where we need to be, and we need some other triangles. The next triangle that we're also going to use is this triangle here. Okay, now to get an equation for theta 2, I'm going to use the tangent. Tangent is opposite over adjacent. The opposite side is the X position of the end effector, and the adjacent is this side right here. I'm going to give that a name. Let's call it R1. So the tangent of theta 2 is the X position of the end effector divided by R1. How could we find a value for R1? We could use the Pythagorean theorem. We could say that R1 squared plus X02 squared is equal to the hypotenuse squared, and here the hypotenuse of the brown triangle is A3. I'm going to solve this equation for R1. I'm going to label this equation 1, then I'll solve the tangent equation for theta 2, and I'll call this equation 2. Numbering these equations can help us keep track of what order we need to put these equations into our code. For example, we can start by solving for R1 in our code. Then we'll have a value for R1 that we can plug into equation 2 to solve for theta 2. But of course, we couldn't do this the other way around. If we try to solve for theta 2 first, we won't have a value for R1. All right, I still need an equation for D1. To get D1, let's try writing an equation like this. Z02, that is the entire distance of the bottom of the purple triangle, is equal to A1 plus D1, that's the distance from the first joint to the second joint, plus R1. Now I'll solve this equation for D1. Since we've already found the value for R1 in equation 1, I can stop here and call this equation equation 3. When I put this into my code, as long as I put these equations in this order, 1, 2, 3, we'll be able to solve for theta 2 and D1 given the values of the link lengths and the position of the end effector only. Okay, are you ready for a more difficult example? Here's the kinematic diagram for the manipulator that we have built on our board. If we can find the inverse kinematics equations here, we can go and put these equations into our PSoC code and see if we can actually position the end effector where we want it. Let's start by drawing this kinematic diagram from the top-down view. The first joint will look just like a circle. Then I want to draw theta 1 at a 45-degree angle. Then we have the second joint also looking like a circle. Now I'll draw the next link for theta 2 also being not 0, but I'm not going to quite draw it at 45 degrees, otherwise the link will be going straight up and that will make it hard for me to see. So I'm going to draw it like this instead. This is the x0 direction and this is the y0 direction. We won't see z0 because that's coming straight out of the page towards our eyes. The theta 1 angle is right here. And the theta 2 angle is here. This link length is A2, and this link length is A4. I'll start by drawing the triangle that shows me the position of the end effector. This distance here is the Y position of the end effector in the base frame. And this position here is the X position of the end effector in the base frame. The other triangle that will help me solve this problem, I'm going to draw in brown. That triangle is this one. The purple triangle is a right triangle, and the brown triangle is not a right triangle. Remember that there are two triangle relationships I can use for right triangles, the Pythagorean theorem and SOHCAHTOA, and one triangle relationship, the law of cosines, that I can use on triangles that are not right triangles. Let's start by using the Pythagorean theorem. The length of this side, which is overlapping between the two triangles, I'm going to call R1. We'll solve for the length of that side by going x02 squared plus y02 squared is equal to R1 squared. And then I'll solve for R1. I'll call this equation equation 1. Now that I know the value of R1, let's look back at the brown triangle, the one that is not a right triangle. In that triangle, I know the lengths of all three sides, and because of that, I can use the law of cosines to find the values of angles. In order to make use of the law of cosines, I need to label a couple new angles. Let's call this angle right here phi1. Let's call this entire angle in the purple triangle phi2. Now I can use phi1 and phi2 to write a relationship with theta 1 like this. theta 1 is equal to phi 2 minus phi 1. If I can get expressions for phi 1 and phi 2, I can find theta 1. Let's start by getting phi 2 from the purple triangle using a tangent relationship. And then I'll solve this equation for phi 2. Next, we want to get phi 1. Phi 1 is inside the brown triangle, and A4 is the side that is across from phi 1. So we can use the law of cosines to get phi 1 like this. We start with the side across from the angle we're looking for. Then we square both of the other two sides, which in this case is R1 and A2. Minus 2 times each of the other sides times the cosine of the angle that we're looking for, which is phi 1. Now I just have to solve this equation for phi 1. Now we can go back and number our equations. We've already solved for R1. This will allow us to go and solve for phi 1. And we can also solve for phi 2. Once we have phi 1 and phi 2, we can solve for theta 1. To find theta 2, I need to mark one more important angle in this triangle. I'm going to zoom in, and I'm going to call this angle right here phi 3. Now, notice that phi 3 plus theta 2 makes a line that is straight. So phi 3 plus theta 2 is 180 degrees. Let's write that down. So we can say that theta 2 is 180 minus phi 3. If we could find an expression for phi 3, we would have theta 2. How could we get phi 3? Phi 3 is one of the angles inside the brown triangle, which is not a right triangle, so we can use the law of cosines. To use the law of cosines to get phi 3, we'll start by finding the length of the line that is opposite phi 3. The length of the triangle side that is opposite phi 3 is R1. So we'll do R1 squared is equal to, now we need the lengths of the other two sides, A2 and A4. A2 squared plus A4 squared minus 2A2 A4 cosine the angle we're looking for, phi 3. Let's solve this for phi 3. All right, the last equation that we numbered was equation 4. So let's call this equation 5. Finally, once we've found the value of phi 3, we can use this equation 6 to find theta 2. I know this was a lot of trigonometry and algebra to get these equations. Don't worry if you don't think you could do this on your own yet. We'll practice this a bunch, both in Robotics 1 and in Robotics 2, until you feel comfortable with it. Right now, we're going to take these equations into our code, and I'm going to show you how to use these equations to position the end effector. Start by opening PSoC Creator and open up the project that we were working with last time. Remember that this project is called servos. The C code in the servos project simply sets two angles to the two servos. That's still what we want to do, except now we want to use our inverse kinematics equations to calculate which angles these should be given a desired x, y position of the end effector. Go up to the beginning of main and let's create two variables to serve as input where we want the end effector to be. Let's just call them x and y. For now, let's just set them equal to 1. We'll go back and change them after we finish writing our code. We'll make these two variables floats so that we could give them decimal points if we want to. Now, we want to enter the equations that we derived previously. We need to start with equation 1 and work through to the last equation, which for us is equation 6. Equation number 1 calculates the value of R1. So we need to create a variable to hold R1. Now, let's go ahead and calculate it. Our equation says that R1 is equal to the square root of x squared, we'll just do x times x, plus y squared, y times y. Now you'll notice that we get a warning here. It says that we've implicitly declared the library function square root. Square root is not a function that is included in project.h. It's included in another library called math. So up here we need to do include math.h. Then we also need to go to project, build settings, and in the assembler, click on general, and then where it says additional include directories, type M and hit enter. M stands for math. We need to do this also in the compiler. So go to compiler, general, additional include directories, type M and hit enter. And we'll do this in the linker also. Linker, general, additional libraries, M, enter, and then additional library directories, M, enter. Then click OK. Now, to make sure that this worked to get square root recognized, let's go ahead and build this program. Now, I get a warning that says R1 is set but not used. That's okay because we haven't yet put in the lines that use R1. So as long as you didn't get any errors and you have a green bar now next to R1, we're still good to go. I'm going to mark this and say that this is equation 1 from our derivation. Let's move on to equation 2. Equation 2 calculates the value of phi1. We have to use the arc cosine, and thankfully that's a function built into the math library. It is a cos. We're taking the arc cosine of a4 squared minus a2 squared And I'm going to put some extra parentheses around here to make sure that we are doing these things in the right order. Minus R1 squared. Then we have to divide this whole thing by -2 times A2 times R1. Now we have to make sure that all these new variables that we've used, we go back up to the top and declare them. So phi1 is a new variable. Let's do float phi1. Then we need A2 and A4. We previously measured A2 and A4 and put it into our Python code when we were doing forward kinematics. So we don't have to remeasure this again. Let's just use values we got and put into our Python code. Okay, looks like we're done with equation 2. Let's move on to equation 3. Equation 3 calculates phi2 using the arctangent. So we need to go back up and declare phi2. All right, on to equation 4. Equation 4 calculates T1 by taking phi2 minus phi1. And we have to go back up here and declare T1. Note that T1 is in units of radians. It's important for us to note that T1 is in radians because our theta1 and theta2 functions here take as input the value of the angle in units of degrees, so we'll need to convert. Okay, on to equation 5. Equation 5 calculates phi3 using the arc cosine. I'm going to start by copying our calculation of phi1 since that one also used the law of cosines. This will reduce the number of things I need to type out. Let's change this to phi3. Then this should be R1 times R1 minus A2 times A2 minus A4 times A4, and then divided by -2 times A2 times A4. There we go. This is equation number 5, and we haven't yet declared phi3, so let's go up and do that. Float phi3 like that. And we only have one equation left here. We've got T2 is equal to, we put 180 minus phi3. However, let's keep in mind that this phi3 is actually in units of radians. So I don't want to use 180 here. I better use pi. 3.14159 will be plenty close for our purposes. Then let's go back up and declare T2. Okay, now the two angles that we want to send the servos to will be T1, and we need to convert that to degrees. So it's going to be T1 divided by pi times 180. And we'll do the same here. Theta 2 should be T2 divided by pi times 180. Let's build this and see if we have any errors. Build succeeded. Now, back here in our build, we need to make sure that the XY position we're commanding the end effector to go to is a position that actually is within its workspace. So let's start by positioning the end effector in a position that's easy to reach. In other words, it's not anywhere near the end of the limits of the servos. So here's an example of one position that it can easily reach. The X position is 1, 2, 3, 4, 5, 6, and the Y position is 1, 2, 3, 4, 5, 6, 7, 8. We're going to try to go to 6, 8. Back in the code, let's enter 6, 8 for XY. Then plug in the USB cable. And program the PSoC. And let's look at what position the end effector goes to. It went to 1, 2, 3, 4, 5 approximately in X, and 1, 2, 3, 4, 5, 6, 7, 8 point something in Y. So our X position is off by about a centimeter, and our Y position is off by a fraction of a centimeter. Let's try another position. Let's see if we can get the end effector to move 2 centimeters to the right of where it is right now. Change x equals 6 in your PSoC code to x equals 8. And then program the PSoC. It did move about 2 centimeters to the right. Let's try and move it back to the left. We'll change the x from 8 back to 6. Program the PSoC. There we go. And now let's go back again. Change the x to 8. Let's see if we can make it go 2 less in y. Let's change y to 6. Now, keep in mind that you can't try to go to an XY position that is outside the robot workspace. For example, let's try going to X15, Y15. That's somewhere way up here. When you do that, nothing happens. In fact, the servos aren't even trying to hold their position. Sometimes when you try to go outside the workspace, the servos will react by doing nothing. Other times, they'll react by kind of freaking out and jerking all over the place. So you have to be careful to make sure that you don't command the robot to try and go outside of its workspace. Also, it's possible to try and tell the manipulator to go to a position that is beyond its range. Okay, we're getting pretty close here to our goal of being able to make a pick-and-place manipulator. This concludes our study of kinematics in Robotics 1. Our next unit is going to be sensors and machine vision. We'll be using machine vision to detect the location that we want the end effector to move to automatically. We'll also be learning in the sensors unit about how to read sensors that will be used to make our prismatic joint, the rack and pinion, be able to move so that it can go up and down to pick an object up.